Welcome! In this session, we will dive into LeetCode problem number 858, mirror reflection. This intriguing problem challenges us to determine which receptor a laser beam will hit after bouncing off the walls of a square room. Let's break it down step by step and explore the best approaches to solve it. Imagine a square room with mirrors on each of its four walls. The dimensions of this room are p x p. Now, a laser is placed at the bottom left corner of the room, which is represented as the point 0, 0. In this setup, there's a receptor located at one of the other three corners of the square, P, 0, P, P, or 0, P. When the laser is turned on, it travels at a 45-degree angle and bounces off the walls of the room until it eventually hits one of these receptors. Your task is to determine which receptor the laser will hit first. The output should be 1 if it hits the receptor at P0, 2 if it hits the one at P, or 0 if it reaches the receptor at 0, P. Let's look at an example to make this clearer. Suppose the room has dimensions where P equals 2 and the distance Q equals 1. When the laser starts at 0, 0, and travels at a 45-degree angle, it first hits the top wall at the point 1, 2. From there, it reflects downward and continues bouncing off the walls as it travels. Eventually, the laser reaches the receptor at the top right corner, P, which is 2, 2, in this case. Since the laser stops at this receptor, the output is 2. Now consider another example where P equals 3 and Q equals 1. Here, the laser reaches the receptor at P0, or 3, 0, without needing additional reflections. Therefore, the output for this case is 1. To summarize the constraints and edge cases, the side length of the room, P, can range from 1 to 1000, and the distance Q, which determines how the laser moves vertically, can be between 0 and P. If Q equals 0, the laser will immediately hit the receptor at P0, resulting in an output of 1. On the other hand, if Q equals P, the laser will directly reach the receptor at P, with an output of 2. For a very small room, such as when P equals 1 and Q equals 1, the laser immediately reaches P again. Finally, for large values of P and Q, like P equals 1000 and Q equals 500, the solution must be efficient enough to handle these calculations without performance issues. This ensures the program works correctly even for extreme scenarios. To solve the mirror reflection problem, we need to determine which receptor the laser beam will strike after reflecting off the walls of a square room. The room is a pxp square with receptors positioned at P0, P, and 0, P. The laser starts from the bottom left corner, 0, 0, and travels at a 45-degree angle. A critical observation here is that the laser moves in a straight line path, and its trajectory can be modeled by imagining the room as repeatedly reflected to form an extended grid. One approach to solving this is simulating the laser's reflections within the room. Each time the laser hits a wall, its direction changes. Specifically, if the laser encounters a vertical wall, its x direction reverses, and if it hits a horizontal wall, the y direction flips. By tracking the laser's position after each reflection, we can check if it has reached one of the receptors. While conceptually straightforward, this brute force approach involves simulating each reflection step by step, which can be computationally expensive. The brute force method has a time complexity of O(k), where k represents the number of reflections required for the laser to hit a receptor. It also uses O(1) space, but the inefficiency arises from having to simulate every reflection individually. This makes the approach impractical, especially for larger dimensions of the room. To address this inefficiency, we can take advantage of the mathematical structure of the problem. Instead of simulating reflections, we can model the laser's trajectory as if the room was extended into an infinite grid. This approach allows us to treat the laser's path as a straight line intersecting specific points in this grid. By identifying the first intersection of the laser's path with one of the receptors, we can efficiently determine the solution without simulating each reflection. The optimized approach relies on several key observations. First, since the laser travels diagonally, its trajectory can be represented as the line y equals x. Second, we can conceptualize the room as being infinitely repeated in a tiled pattern of pxp squares. In this extended grid, the laser reaches a receptor when it intersects a point m*p, n*p, where both m and n are integers. The receptor it strikes depends on the parity of m and n. Specifically, if m is even and n is odd, the laser will hit the receptor at p0. If both m and n are odd, the receptor at p is hit. Finally, if m is odd and n is even, the receptor at 0, p, is hit. To determine the values of m and n, we calculate the least common multiple, LCM, of p and q. From there, we compute m equals LCM, p, q, slash p and n equals LCM, p, q, slash q. Based on the parity of these values, we can quickly determine which receptor the laser will strike. This approach has a time complexity of O log min p q for calculating the LCM and requires constant space, making it highly efficient. The optimized approach was chosen because it avoids the inefficiencies of simulation and instead leverages the mathematical structure of the problem. By reducing the solution to a simple calculation involving the LCM and the parity of m and n, it achieves high efficiency with minimal computation. This method is particularly advantageous for large values of p and q, as it operates in logarithmic time relative to the room dimensions. Additionally, the optimized approach is conceptually elegant, eliminating the need for iterative simulation and handling edge cases, such as when p and q are coprimorph multiples of each other, with ease. However, it does require some understanding of modular arithmetic and the properties of the LCM, which might be less intuitive for some. In contrast, the brute force approach, while simpler to understand, is computationally expensive and impractical for larger inputs. Ultimately, the optimized approach stands out for its clarity, efficiency, and scalability, making it the ideal solution for the mirror reflection problem. To solve the problem, we need to understand the setup of the square room and how the laser beam behaves. The room has dimensions pxp, and the laser starts at the bottom left corner, 0, 0, traveling at a 45-degree angle. As it moves, it bounces off the walls of the room until it hits one of three receptors located at p, 0, p, p, and 0, p. Our goal is to determine which receptor the laser beam reaches first. Instead of explicitly simulating the laser's reflections within the room, we can simplify the problem using the mirrored room method. By imagining the square room as being infinitely repeated through mirroring, the laser beam can be treated as traveling in a straight line through this grid of mirrored rooms. This approach eliminates the need to calculate each bounce individually, reducing the problem to finding the point where the laser intersects one of the receptors in the mirrored grid. With the mirrored room model in place, we can now formulate the problem mathematically. The laser beam travels along the line y equals x, as it starts at 0, 0, and moves at a 45-degree angle. To find where the laser hits a receptor, we need to identify the first point of intersection between this line and the receptors in the mirrored grid. The receptors in the mirrored grid are located at kp, 0, kp, kp, and 0, kp, where k is a positive integer representing the mirrored room index. The task is to find the smallest intersection point, MP, NP, such that both m and n are integers, and the condition m equals n holds, since the laser travels along y equals x. The smallest intersection is determined by finding the lowest positive m4 which both x equals mp and y equals np align with the receptor's coordinates. This boils down to solving for m as the least common multiple, LCM, of p and 1, which simplifies to p in this case, given that p is the room's dimension. Once we've determined the smallest value of m, we can identify which receptor the laser hits based on the coordinates of the intersection. If m is even, the laser hits the receptor at p0, which is receptor 1. If m is odd, we need to check the coordinates further. If the y-coordinate at the intersection equals p, the laser hits p, which is receptor 2. Alternatively, if the x-coordinate equals 0, the laser hits 0, p, which is receptor 3. This logic allows us to determine the receptor hit using a simple parity check. The mirrored room method simplifies the problem to a geometry question, where the first intersection corresponds to the smallest m that satisfies the conditions. By focusing on the LCM of p and checking the parity of m, we avoid iterative calculations and directly identify the receptor hit. The beauty of this solution lies in its simplicity. No complex data structures are needed, everything relies on arithmetic operations. The mirrored room model, combined with the use of LCM and parity checks, ensures the calculations are efficient and straightforward. The key operations involved include computing the LCM of p and 1, which is trivial as it simplifies to p, using modulo operations to check whether m is even or odd, and validating which receptor the intersection corresponds to based on its coordinates. In terms of complexity, the solution is highly efficient. The time complexity is O(1), because the computations involve only a few arithmetic steps, and the space complexity is also O(1), as no additional space is required beyond a few variables. This makes the algorithm not only elegant but also optimal for solving the problem efficiently. This Python solution solves the mirror reflection problem using a mathematical approach based on the least common multiple, LCM. The laser beam's behavior is periodic, and calculating the LCM of P and Q allows us to determine when the laser aligns with a receptor. The code starts by finding the LCM of P and Q using the greatest common divisor, GCD, method. This involves a loop where the GCD is calculated iteratively. Once the LCM is determined, the number of extensions, horizontal movements, and reflections, vertical movements, are calculated by dividing the LCM by P and Q, respectively. The solution then evaluates the parity of these counts. If the number of extensions is even, the laser hits receptor 0. If the number of reflections is odd, it hits receptor 1. Otherwise, it hits receptor 2. This concise and efficient implementation avoids simulation and directly computes the result using mathematical properties, ensuring optimal performance. Here, we begin by defining the mirror reflection method, which takes two parameters, P and Q. These represent the dimensions of the square room and the distance the laser travels vertically, respectively. The first step in the implementation is to calculate the greatest common divisor, or GCD, of P and Q. This is done using a helper method we'll define shortly. Next, we calculate the least common multiple, or LCM, of P and Q. The LCM helps us determine the smallest point where the laser's horizontal and vertical paths align. To calculate it, we use the formula P*Q/GCD. Once we have the LCM, we determine the number of extensions and reflections by dividing the LCM by P and Q, respectively. This tells us how many times the laser extends across the room horizontally and reflects vertically. Now, the key logic follows. If the number of extensions is even, we know the ray hits receptor 0. Otherwise, we look at the parity of the reflections. If the reflections are odd, the ray will hit receptor 1. If they are even, it will hit receptor 2. Finally, this method returns the corresponding receptor number based on these conditions. To support the main logic, we define a helper method called GCD to calculate the greatest common divisor of two numbers. This method uses the Euclidean algorithm. The process involves repeatedly setting b to the remainder of a divided by b, and then swapping the values of a and b until b becomes 0. At that point, the value of a is the GCD of the two numbers. This helper function allows us to efficiently compute the GCD, which is essential for determining the LCM and ensuring the correctness of our solution. Once this helper method is in place, the implementation is complete, and we can solve the problem using the logical steps we've outlined. We start with a square room of size 2 by 2, where the laser beam begins at the bottom left corner and travels at a 45-degree angle. The goal is to determine which receptor the beam will hit, receptor 0 at the bottom right, receptor 1 at the top right, or receptor 2 at the top left. First, we compute the greatest common divisor, or GCD, of the room size P and the slope factor Q. Here, P is 2 and Q is 1. Using the Euclidean algorithm, we repeatedly update m and n by assigning n to m and m% n to n, until n becomes 0. For P equals 2 and Q equals 1, this gives us a GCD of 1. The next step is to calculate the least common multiple, or LCM. The LCM is determined by the formula P*Q/GCD. Substituting the values, we get 2 by 1/1 equals 2. This value represents the smallest distance where both dimensions align. Finally, we calculate the number of extensions and reflections. Extensions are determined by dividing the LCM by P, giving 2/2 equals 1. Reflections are determined by dividing the LCM by Q, giving 2/1 equals 2. Now, we use the calculated extensions and reflections to determine which receptor the beam will hit. If the number of extensions is odd and the number of reflections is even, the beam will reach receptor 2. Here, the extensions count is 1, which is odd, and the reflections count is 2, which is even. Thus, the beam hits receptor 2. For this example, the output is receptor 2. Moving on to a slightly larger room with a different slope, we now consider P equals 3 and Q equals 2. The room is now 3 by 3, and the beam moves at a slope of 2:1. Again, we compute the GCD. Starting with m equals 3 and n equals 2, applying the Euclidean algorithm, we perform the steps m n equals n, m%n, which gives m equals 2 and n equals 3% 2 equals 1, and then m equals 1 and n equals 2% 1 equals 0. Thus, the GCD is 1. With the GCD calculated as 1, we move to the next step of finding the LCM. Using the formula P*Q/GCD, we substitute P equals 3 and Q equals 2 to get 3 by 2/1 equals 6. This means the LCM for this setup is 6. From here, we determine the number of extensions and reflections. Extensions are calculated as LCM/P, giving 6/3 equals 2. Reflections are calculated as LCM/Q, giving 6/2 equals 3. To decide the receptor, we analyze the parity of these values. If the extensions count is even, the beam ends up at receptor 0, which is at the bottom right corner. Here, extensions are 2, which is even. Therefore, the beam hits receptor 0. The output for this example is receptor 0. Next, let's explore another example where the room size is 4 times 4 and the slope is defined by P equals 4 and Q equals 3. In this example, the beam travels through a 4 by 4 room and follows a slope of 4:3. To determine the receptor, we first compute the GCD of P equals 4 and Q equals 3. Using the Euclidean algorithm, we start with m equals 4 and n equals 3. The sequence of steps is m n equals n, m%n, which gives m equals 3 and n equals 4% 3 equals 1, and then m equals 1 and n equals 3% 1 equals 0. The GCD is 1. Next, we calculate the LCM using P*Q/GCD. Substituting P equals 4 and Q equals 3, we get 4 by 3/1 equals 12. This value represents the smallest distance at which the beam aligns with both room dimensions. Now, we calculate the number of extensions and reflections. Extensions are determined by dividing the LCM by P, 12/4 equals 3. Reflections are determined by dividing the LCM by Q, 12/3 equals 4. Finally, we decide the receptor by analyzing the parity of extensions and reflections. If the number of extensions is odd and the number of reflections is even, the beam will hit receptor 2, located at the top left corner. Here, the extensions count is 3, which is odd, and the reflections count is 4, which is even. Therefore, the beam reaches receptor 2. The output for this example is receptor 2. Through these examples, we've seen how to determine the receptor by breaking the problem into clear steps, finding the GCD, calculating the LCM, and analyzing the number of extensions and reflections. This systematic approach ensures that we can solve any instance of the mirror reflection problem efficiently. To analyze the time complexity of the solution, we can break it into distinct steps. First, we have the computation of the greatest common divisor, or GCD, using the Euclidean algorithm. This process involves repeatedly performing modulo operations until the remainder becomes 0. The number of operations in the worst case is logarithmic in relation to the smaller of the two numbers, p and q. This gives us a time complexity of O log min p q. Next, once we have the GCD, we calculate the least common multiple, or LCM, using the formula P*Q/GCD. This calculation involves a single multiplication and division, both of which are constant time operations, so this step is O(1). Lastly, determining the number of extensions and reflections involves dividing the LCM by P and Q. These are also constant time operations, O(1), since they are simple divisions. The final step in the solution involves a couple of conditional checks to determine whether the number of extensions and reflections is even or odd. These parity checks are also constant time operations, O(1). Now, when we combine all these steps together, the dominant factor in the time complexity comes from the GCD computation, which is O log min p q. Since all the other operations contribute just O1 each, the overall time complexity of the solution is O log min p q. On the space complexity side, let's start with auxiliary space. The solution uses a fixed number of variables, such as m, n, LCM, extensions, and reflections. These are all single integers, and their memory usage does not scale with the size of the input. Additionally, the Euclidean algorithm is implemented iteratively, so there's no recursive stack space involved. This means the space complexity is constant, or O1. When we consider the overall space complexity, it is clear that the memory usage remains independent of the size of the input. As a result, the space complexity is O1. To compare this solution with a brute force approach, imagine simulating each extension and reflection step by step until the laser reaches a receptor. This would require iterating through multiples of p and q to find their least common multiple. The time complexity for this naive approach would be O p asterisk q, which is significantly worse than the efficient O log min p q solution we've achieved here. The key advantage of the current solution is that it avoids explicitly simulating the process by leveraging the mathematical properties of the GCD and LCM. This drastically reduces the number of operations required, making it far more efficient. The mathematical proof of the time complexity lies in the behavior of the Euclidean algorithm. Each iteration of this algorithm reduces the size of the problem by at least half. This means the number of iterations required is proportional to the logarithm of the smaller input, log min p q. Since all the other operations, such as LCM computation, division, and parity checks, are constant time, these do not affect the overall asymptotic complexity. When we analyze the best, average, and worst cases, we see that the complexity remains O log min p q across all scenarios. The best case occurs when p and q are small, leading to fewer iterations in the GCD computation, while the worst case involves larger values of p and q. However, the logarithmic nature of the algorithm ensures efficiency even in the worst case. Throughout all cases, the space complexity stays constant at O1, reaffirming the efficiency of this approach. When tackling this problem, there are a few common mistakes that can trip you up. First, many people assume that solving this problem requires simulating infinite laser bounces. This approach is unnecessarily complex since the problem can actually be simplified using geometric insights, such as finding the least common multiple or applying modular arithmetic. Another frequent issue is mishandling edge cases, particularly when the length of the side p is a multiple of q. In these situations, the laser often hits a receptor directly, and ignoring this can lead to incorrect results. Finally, some overcomplicate the geometry by attempting to manually track the laser's path through every reflection. This approach not only increases the likelihood of errors but is also unnecessary, as the solution can be derived algebraically without explicitly tracing the beam's trajectory. Another pitfall is confusing the coordinate positions of the receptors. Misidentifying which receptor corresponds to P0, P, or 0P can easily lead to inaccurate outputs. It's essential to map the final coordinates to the correct receptor to ensure the solution is accurate. Additionally, performance considerations are critical when P and Q have large values. Brute force methods that simulate the laser's reflections iteratively are computationally expensive and can result in timeouts. Instead, leveraging efficient techniques like using the greatest common divisor, GCD, and least common multiple, LCM, ensures optimal performance, even for large inputs. To excel in interviews, recognize that this problem can be reduced to a number theory solution involving the least common multiple. By scaling the room geometrically, you can map the laser's path without needing to simulate each bounce. The key pattern is that the laser will hit a receptor when it reaches a corner of the grid. By scaling the room dimensions, the receptor can be determined by analyzing the parity of the scaled coordinates. Optimization comes from leveraging LCM, P, Q, to compute the number of reflections algebraically, which efficiently determines the laser's path along the boundaries. It's also vital to address edge cases where P equals Q or Q is 0. These cases often simplify the problem and should be handled explicitly to avoid errors. This problem, LeetCode 858, provides excellent practice for applying number theory and geometric reasoning. To further strengthen your skills, consider related problems like LeetCode 343, the integer break problem, which focuses on mathematical optimization and breaking problems into smaller, manageable components. Another interesting challenge is LeetCode 365, the water and jug problem, which also uses GCD and LCM concepts to find efficient solutions. Lastly, while not directly related to geometry, LeetCode 470, implement RAN 10 using RAN 7, is a great problem for understanding how to reduce simulations into mathematical calculations, reinforcing your problem-solving abilities across different contexts. There are several approaches to solving this problem, each with its own advantages and trade-offs. A brute force simulation involves tracing the laser's path by iteratively reflecting it within the room. While this method is intuitive and works well for small values of P and Q, it becomes inefficient for larger inputs due to its high time complexity. A more efficient approach is geometrical scaling using the LCM. By scaling the room dimensions, you can determine the laser's final position without explicitly simulating the reflections. This method is highly efficient, with a complexity of O, log, min, p, q, when using GCD and LCM, though it requires a solid understanding of number theory to implement correctly. Lastly, a less common but more generalized approach is to represent the reflections as matrix transformations on a coordinate system. While this method can handle different shapes and scenarios, it's overkill for this specific problem and more challenging to implement. Thank you for joining me on this journey through problem number 858, mirror reflection. We summarized the key algorithmic insights, discussed its complexity, and highlighted important takeaways. If you found this helpful, please like and subscribe for more problem walkthroughs. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!